One of the dumbest traditions in astronomy is the use of a single word to represent everything that orbits around a planet. Whether that word is the technical term natural satellite or the more colloquial term moon, describing all planet-orbiting objects this way ignores their geophysical diversity and leads to confusion and numerous misconceptions. Indeed, when most people hear the word moon, they think of Earth's moon and its physical characteristics. So when they hear that Jupiter has 97 moons, they tend to picture our large celestial neighbor as having 97 versions of what we see in our sky. But this is far from the reality, in which only 4 of its 97 moons are large spherical bodies like Luna, and the rest are potato-shaped boulders, dozens of times smaller and thousands of times less massive. In fact, the mass of Jupiter's 4 spherical Galilean moons represent 99.997% of all the mass orbiting that planet, leaving the remaining 93 some odd satellites to make up a combined 0.003%. Because of the significant differences between these two types of moon, some scientists and science communicators have begun using the terms major moons and minor moons to distinguish between them. Major moons are the massive spherical bodies like Luna, Ganymede, and Titan, and represent the smallest population, with only a couple dozen existing in a planetary system. Minor moons are the diminutive, asymmetrically shaped objects like Phobos, Almathea, and Hyperion, and represent the vast majority of the satellites in a planetary system, numbering in the hundreds. These differences in size and mass lead to the two populations of moons having very different properties. Major moons can potentially have atmospheres, while minor moons cannot. Major moons can have complex, differentiated interiors with multiple geological layers and possess seismic and volcanic activity, while minor moons are typically nothing more than giant boulders or spherical piles of rubble. Major moons are always tightly locked to their parent planet, but minor moons can possess independent or chaotic rotations. And major moons have significant gravitational fields that interact with their parent planet and sibling moons, while the low mass of minor moons makes their gravitational influence negligible. So when discussing the moons of a planet, it is very important to specify what type of moon is being talked about. Beyond their mass and shape, we can further classify moons by the type of planet that they form around, giving us terrestrial moons and Jovian moons. Moons form around Jovian planets through the process of co-accretion, very similar to the way planets form around a star. As the planet itself is forming, it gathers a disk of gas and dust in orbit around it, from which its moons will form. As they grow in mass and get larger, they interact with more of the disk and experience a drag force that saps energy from their orbit and causes them to migrate closer to the planet. Eventually, they reach their Roche limit and are torn apart, with some of their mass being absorbed into the planet and the rest being scattered back out into the disk. This continues through multiple generations of moons until the disk is depleted of the majority of its material and the drag force disappears, leaving some number of surviving major and minor moons. The more massive the parent Jovian planet, the larger and more massive the moon-forming disk can be, and as a result, the higher in mass the moons forming within it can potentially be. But this also imposes an average mass ratio between the parent body and its moons of approximately 10,000 to 1. This means that each moon orbiting the planet will likely be at least 10,000 times less massive than the planet. All of Jupiter's moons have mass ratios above 10,000 to 1, including Ganymede, the largest moon in the solar system, which is 12,809 times less massive than Jupiter. This is also true of all of Uranus's moons and all but one of Saturn's moons. Saturn's aptly named moon Titan and Neptune's solitary major moon Triton are the only exceptions, having mass ratios of approximately 4,225 and 4,788 to 1, respectively. Moons possessing such a low mass ratio with their parent planet are extremely rare. So if you place such a high mass moon around a Jovian planet, all additional moons of that planet should be well above the typical 10,000 to 1 mass ratio. Science fiction authors and world builders often make the mistake of placing Earth mass moons around a Jovian planet that is analogous in mass to Jupiter or Saturn, or sometimes even smaller. Not only is this unrealistic in terms of the way Jovian moons form, but it is also unstable. If we look at Saturn and Titan's relationship, we find that the shared center of mass that they both revolve around as they orbit lies only 289 kilometers from the center of Saturn. So, relative to the other orbiting moons, Saturn shifts less than 600 kilometers over the period of one Titan orbit. But if Titan instead had a mass equal to that of Earth, Saturn would shift by over 25,000 kilometers, causing the other moons that orbit it to develop extreme eccentricities that would ultimately destabilize the system of satellites. If you need your fictitious moon to have a mass close to that of Earth, then you should ensure that your Jovian planet is at least 4,000 times more massive than the most massive moon, and preferably a lot higher than that. Jovian moons will additionally come in two subtypes based on their geophysical compositions, being either rocky or icy. If your Jovian planet lies in the inner region of the planetary system, then its moons will likely have a predominantly rocky composition, perhaps with a small metallic core, giving them a mean density lying between 3,000 and 5,000 kilograms per cubic meter. If your Jovian planet lies in the middle or outer region of the planetary system, then its moons will likely have a predominantly icy composition with a rocky core, and a mean density somewhere between 800 and 3,000 kilograms per cubic meter. Terrestrial planets lack the mass necessary to form moons through co-accretion like Jovian planets do. Instead, terrestrial planets can only form moons through collision events. In such events, either the impacting object is destroyed in the collision and its ejecta coalesces to form the planet's moon, or the impacting object has some amount of its outer mass sheared off in the collision and its remains lose enough angular momentum to enter orbit around the planet. These events can lead to a terrestrial planet having multiple minor moons, since these bodies have comparatively insignificant gravitational masses and are often scattered widely by the collision that formed them, leaving them distant enough from one another to be stable over geological timescales. However, such events can only form one major moon around a terrestrial planet. This is because the material thrown into orbit around a planet following a collision event occupies similar orbits and thus will ultimately coalesce into a single object. And once that first major moon is formed, it dominates the orbital space around the planet. If any more collision events take place, the material thrown into orbit gets either absorbed or scattered by the existing major moon, preventing any additional major moons from forming. Even if some unlikely event took place that led to the formation of two major moons around a terrestrial planet, tidal interactions between the two moons and their parent planet would ultimately destabilize the system, resulting in the collision or ejection of one of the major moons. Now, I've been using the terms major moon and minor moon for simplicity and clarity, but it's important to point out that the type and shape of the moon is irrelevant. Only the mass of the moon matters in this formation scenario. So, as a rule of thumb, a terrestrial planet will only have one moon with a mass greater than 10 to the 17 kilograms. All additional minor moons should be well below this mass limit. This is often one of the hardest pills for authors and world builders to swallow, as science fiction has spent the past several decades convincing people that a planet having only one major moon, as Earth does, is mundane and boring, and that a truly interesting alien world is going to have several spherical moons filling its sky. This notion not only fails to match our physical reality, but also denigrates the significance of Earth's lone major moon. Most terrestrial planets do not have any moons. Of those that do, the majority have only minor moons. A terrestrial planet having a major moon is quite rare and one of the things that actually makes our home planet extraordinary. Building major moons is pretty straightforward and not much different than building terrestrial planets. I have previously made a video explaining how to do that, so I will just link it here and in the video description below. For major moons whose properties aren't necessarily important to your fiction, I would recommend building them like subterrestrials. First, define their mass, making sure that it is more than 10,000 times less than its parent planet, and use the mean density that we discussed earlier, depending on whether the moon is predominantly rocky or icy. But for moons whose properties need to be specific, I would recommend building them like terrestrials. Define the surface gravity that you want them to have, and then use the mean density that corresponds to their composition, again making allowances for the mass ratio with their parent planet. Part 2 of this video will cover placing your major moon into orbit of the planet. I hope you will join me for that.